Hello everyone. Today our topic is time period of SHM. In the last lectures, we have discussed about the equation of SHM that F is equal to minus Kx. Okay. And what is F here? F is the net restoring force. Net restoring force. We have already discussed about this. And here X is the displacement from mean position. Displacement from mean position, and K is SHM constant. Okay, this is SHM constant. From this equation, F is equal to minus Kx, we can write A is equal to minus K by M into X. This is we have already discussed this, and which is equal to minus omega square x. This is another equation. Here A is the acceleration of that body which is doing SHM. Omega, we know that omega, that is angular frequency, which is equal to 2 pi divided by t. And what is t here? And this t is time period, that's 2 pi by omega. So this is the time period of SHM. So today our topic is actually time period of SHM. So actually we have to find this t. For finding this t, we should know 2 pi is constant, so we should know this omega of that body which is doing SHM. And for this omega, find this omega, either we need this equation or we need this equation. And what is this F? F is net restoring force on that body, and X is the displacement of body from its mean position. So to find the time period, we actually should know the mean position actually. If we know the mean position, then we can find the displacement from that mean position. If we know that, then we can find the net restoring force. What are the steps to be involved to derive the time period of this SHM? The first step is we should know the mean position. So we have to find, first step is we have to find mean position of body executing SHM. So this is our first step for this. So if we know the mean position, then we can find the X, we can displace the body from its mean position, that is this X. Then we have to find the net restoring force. When we are displacing the body from its mean position from X, then find the net force on that body, net restoring force. So this will be our second step. So second step will be, we have to displace the body through some small displacement, X, then find net restoring force. When you find net restoring force, that will be obviously directly proportional to X, linearly directly proportional to X. So we will find F is equal to some displacement X. So when we find some constant here, this is actually minus Kx, because this restoring force will be always in, actually it's restoring force, so it will be in opposite direction to that of X. So if we found the equation, that is F is related to X, the constant here will give you the value of this K. If you are given with the value of K, that means K by M will give you omega. That means you can find out the time period. Okay. So this is the method. And another method is there, that is called energy method. We can also calculate the time period by energy method, but let's discuss that in another class. So today we have to find the time period by this method. So let's take some examples, illustrations. So how can we find the time period? Okay students, let's take first illustration, which is a very simple illustration. So this is the system where one spring is there whose spring constant is K. It's spring constant, not SHM constant. We have to find that SHM constant. And the mass M is suspended on this from this spring. Now we have to find out the time period. What do you mean by time period? If we displace this M through some small displacement X, for example, I am displacing this like this, then I left it, so it will be doing SHM like this. So what is the time period? So we have to find that. So what was our first step? We have to find the mean position. Students, now tell me, is this the natural length of the spring, or is the equilibrium position? Obviously, it's not the natural length. Natural length means if we remove this m, what will be the length of the spring? It will be the same or it will be less. Obviously, it will be less because this mass, it's the weight of this mass actually it elongated this spring. Okay, so we have to find first the equilibrium position. That's called mean position. So this is actually, we know that some natural length will be here. Its natural length will be here. From natural length, this is its mean position. This is its mean position. Now we have to find this. Here we can find that there is force mg downwards. Now the spring is elongated some x naught. That this elongation will be x naught. So in upward direction there will be force, spring force, that's kx naught, because the spring constant is k. Now here we can say that, is this equilibrium position? Yes, obviously this body is at rest. So we can say that for step 1, we can say that mg downwards is equal to kx naught. So here we found the mean position, that's x naught from natural length, that's mg by k. We can say that x naught as a mean position is equal to mg upon k. Okay. Now the second step, we are going to find the, if we displace this mass, let's take another diagram. So we are displacing this mass through some x from its mean position. This is mean position. Now we are displacing it again some x. Now what is the force here? Net force. We have to find, second step is we have to find net force. So here downward is mg. It's again mg because its mass and weight will be constant. Now in upward direction, from natural length is displaced from is x naught, and from this mean position it's x. So the total displacement is actually its natural length. So it is x naught. The total displacement is x naught plus x. So upward force will be k x naught plus x. Okay. Now are these two forces equal? No. Obviously mg is less than this because mg is equal to kx naught and this is kx naught plus x. So we can say that F net, which is equal to kx naught plus x minus mg. So k x plus x naught minus mg. This is F net, upward force minus downward force, is equal to, F net is equal to, okay, sorry, this is F net. Huh? This is your F net. This minus this, okay? Okay. Now this is kx plus kx naught minus mg is equal to F net. Now from first equation we know that mg is equal to kx naught. Here mg minus kx naught, yeah, kg minus mg, kx naught minus mg, that's equal to 0. Okay, so we can say that F net is equal to kx. F net is equal to kx. Since x is downward direction and F net is in upward direction, we can say that here minus sign, if we say as a vector. So F net is equal to minus kx. Now equating this with the equation of SHM, here F is equal to minus kx. So what is in place of a k? It's again this k. So that means in this case the spring constant k is equal to the SHM constant k. So simply we can write it as acceleration is minus k by m into x. So this is actually omega. So we have find omega is equal to under root a by m. Omega square is actually this. So from here we can find time period, simply that's 2 pi divided by omega. So the time period of this body will be 2 pi under root m upon. So this is the time period. Okay. Now second illustration. Now the second illustration, let's take the second illustration. The question is written on the board. A uniform rod is placed on two spinning rollers. There are two rollers actually. They are spinning and the rod is on them as shown in the figure. Symmetrically. Symmetrically means the center of mass lies at the center of these two rollers. Let the mass of this rod is m, so the weight will be acting here. This is L, this distance is given L, so this will be L by 2 and this will be L by 2 and this distance is again same. That we mean by this symmetry. The coefficient of friction between the rod and rollers is mu. So we are given here is friction between the rollers and rod, here is friction and the coefficient of friction is mu. Both same. Between the rod and the rollers is mu. The final period of oscillation of rod if it is slightly displaced horizontally and released. At this position is actually an equilibrium position. How we can say that? Look, if this is mg, here the force in upward direction, here will be the force in upward direction. Let this be n1 and let this be n2. But we know that mg downwards, these two force upwards, and this n1 and n2 in this case will be same. Why? Because mg is acting at the center. So we can prove that by the torque equation. So we can say that for this equilibrium position, we can say that n1 and n2 they are equal. N1 is equal to n2. So we can actually write here nn. We know that. So let's write nn. So we can simply say that mg is equal to n plus n, that's 2n. So we can say n is equal to mg by 2. But we do not require this because now we have to displace it from horizontally. So we displace it a little bit. So what will happen? Actually, there is another force. There is frictional force here. If the roller is going like this, anti-clockwise, this is going anti-clockwise direction. So the frictional force at this point on this roller will be in this direction, and on the rod it will be in this direction. Similarly, this roller, this is going clockwise direction. So friction force on the roller will be in this direction, but on the rod it will be in this direction. Let this will be F1 and this will be F2. And in this case, it's again same here. Here, if this is symmetric, so it is same. This F will be equal to this F. Why? Because we know force is equal to mu times n. Here n and here n, they is same, so the friction will be again same. But our question is, we are displacing this rod. So what will happen now? We will write another diagram. We will draw another diagram. So now we are displacing it a little bit. So this is our rod. This is one roller. This is another roller. So we have displaced it towards right. So this distance is less than this distance. So here M will be at the center. So it is here mg. This distance is L, but this is not L by 2 now. We have displaced this at distance of x actually. So from this point, this distance will be L by 2 plus x, and from this point, from this center, this distance is L by 2 minus x. Okay. Now here, there will be at this point, here the normal was n, but here it will be some n2 and here it will be n1. So the normals will be different here. Why? Because mg is shifted at this point towards right. So n2 will be obviously greater than n. Okay. So friction will be different here in this case. Here the frictional force, let this be F2, and here the frictional force on the rod, actually we are dealing it on the rod, friction force. So F2 will be again greater than F1. Why? Because N2 is greater than N. So we have to find the time period. So for time period, we have to find net force. So for net force, we can say that F net here, in this case, let's do it on again, another page. So F net will be here. So which one force is greater than? That's F2 is greater than F1. So F net will be F2 minus F1. F net will be equal to F2 minus F1. Now what is F2? F2 is mu times N2. And what is F1? Mu times N1. So we can write that our F net will be mu times N2 minus mu times N1. So this is our F net. But we have to find F net in terms of x, in terms of the displacement, then we can find the time period. So that means we have to find this N1 and N2. For N1 and N2, we have to find N1 and N2. So let's write this point as, let this point be A and let this point be B. So what about A? About A, can we say that the net torque is 0? Yes, because F torque of this force is 0, torque of this N1 is 0, this is crossing through this point. This F2, the line of action is going through this point, so the friction of this F2, sorry, the torque of this F2 is 0. And what about this N2? N2 is going this and there is some distance, so there will be torque. But we know that this rod actually is in it is in rotatory equilibrium. So net torque should be 0. Okay? So we can say that net torque about A should be 0, but in this case, we see that there are two forces, one is N2 and another is mg. There is the torque of mg in this direction, in inverse direction, and there is the torque of N2 in outward direction. So the torque net should be 0. So from there we can find N2. Similarly, about point B, we calculate torque. There are two forces, one is N1 and another is mg. Again, the net torque will be 0 because the rod is in rotatory equilibrium. It's not rotating, so net torque should be 0. So by that we can find N1 and N2. Start with about point A. So it will be torque about A is actually N2 into this length, that's L, and 2 into L, that's in forward direction, and for mg it's mg in inwards, that's mg, and this distance is L by 2 plus x minus mg L by 2 plus x. That is equal to 0. That's equal to 0. Okay. So from here we can find N2. N2 is actually mg L by 2 plus x divided by L. That is your N2. So this was torque about A. Okay. Now we have to find torque about B. Now torque about B, there are two forces. One is N1, another is mg. So what about N1? N1's torque will be N1 into L, and mg's torque will be mg into this L by 2 minus x. So similarly, we can write it, torque about B is 0. That is N1 into L minus mg L by 2 minus x is equal to 0. Similarly, we can say that N1 is equal to mg upon L, L by 2 minus x. So this is the N1 and this is N2. Now put the values of this in this. So we have to find F net. So F net will be equal to mu, that's common. This is N2 minus N1. N2 is this mg by L, L by 2 plus x. And this is N1 minus mg by L, L by 2 minus x. From here we can say mg by L, let it be common, mg by L. So we can take it as F net will be equal to mu mg by L, mu mg by L, and it will be L by 2 minus x minus L by 2 minus plus x. So it's L by 2 minus x, sorry, plus x. Then minus into L by 2 is minus L by 2. And minus into minus will be plus x. So here plus L by 2 and minus L by 2 gets cancelled. So F net comes out to be, this is 2x. So 2 mu mg upon L into x. Okay. Now here F net mu m2. F2, actually it's F2. F2 minus F1. F2 is in this direction, F1 is in this direction. So F net is in this direction and X is in this direction. So we can say that if we take it as a vector, so we can say here it's minus. So they are opposite. Now equating it with equation F is equal to minus kx. So what is the value of k here? That SHM constant, that's 2 mu mg by L. Here the value of k is 2 mu mg upon L. If this is the value of k, we can find omega, we can find time period. So simply time period is 2 pi under root m by k. So the time period will be equal to 2 pi under root m upon k, that's 2 mu mg upon L. So the time period is 2 pi under root L upon 2 mu mg. So this is the answer. Thank you.